is a screencast to take you through the beginnings of regression. And the purpose of this screencast is to show you what regression is, as well as take you through the calculations that you would use to calculate a regression on a really small data set. So when we think about regression, we oftentimes think about correlation as well. And regression is when we estimate the relationship of one continuous variable with another by expressing one in terms of a linear or more complex function of the other. Correlation is just when we're estimating the degree to which two variables vary together. And this is oftentimes referred to as covariance. So they are somewhat different. In one, you're trying to actually develop a statistical model where an x variable might be used to predict a y variable. And in the other situation, correlation, we're just interested in whether or not two variables vary in concert with one another. So when we do regression, it generally takes the form of y equals a plus bx, where b is the slope and a is the y-intercept. So this is your typical definition of a line from high school. And so we have two types of regression. Model 1 regression is also referred to as ordinary least squares, or OLS regression. So if you're ever reading a paper and they say OLS, they're talking about ordinary least squares regression. In this case, generally the independent variable is measured without error. It's under the control of the investigator, and the x variable is fixed. And what an ordinary least squares regression does is it basically tries to find what the expected value is for any given x. And so for any given value of x, y's are going to be, the y variable is going to be independently and normally distributed around the line, and the samples along the regression line are homoscedastic. So these last two things are essentially the normality assumption and the homogeneity of variances assumption in the context of regression. And so the researcher basically varies x, and as the researcher varies x, looks to see how y is changed by varying x. This is different than a Model 2 regression where both x and y are random variables. And even though most people have data that are of this nature, they typically don't do a Model 2 or standard major axis regression. They normally do ordinary least squares regression, even though that's not technically what one should be doing. So, an example. We have water loss in confused flower beetles. I don't know why the flower beetles are confused, but they are called Tribolium confusum because they evidently are confused. And water loss occurs under different conditions of relative humidity, and in this case, presumably relative humidity was set by the investigator. And what the investigator did was it weighed beetles in 9 groups of 25 beetles apiece, and 6 days later reweighed the beetles to register weight loss or gain. And so the independent variable in this case is the relative humidity that was set by the investigator, and the dependent variable is weight loss. Oh, I didn't show you the data actually. Oh, here are the data. So we have relative humidity going from 0% up to 93%, and we have the weight loss of each of the beetles. And when we make a plot of this, it basically looks like this, where it looks like the lower the humidity, the greater the weight loss, the higher humidity, the less the weight loss. And our questions of this data set are, is the relative humidity leading to a loss of weight in flower beetles? And it looks like it is, because it looks like this would have a negative trend. But our purpose in regression is to quantify the degree to which relative humidity is responsible for weight loss and expressing that in a linear relationship. So how do we go about doing that? Well, we begin with many of the things that are familiar to you. We have percent relative humidity, we have weight loss. We can sum up all of the relative humidity. We can arrive at the mean relative humidity for this data set. We can sum up the weight loss and calculate the mean weight loss. So the average relative humidity was 50.389%, and the average weight loss was 6.022 milligrams. And so we can plot where the relative humidity mean is, and we can plot where the mass loss mean is. And where these two lines intersect, presumably the line of best fit is going to pass right through this intersection of the average relative humidity and the average weight loss. But now the question is, how do we go about estimating what that line is? A horizontal line at the average mass loss is the null hypothesis, the null hypothesis being a slope of 0. But when we look at the residuals, the difference between each data point and the average mass loss, we see that the residuals are very high at both low humidity and high humidity. And we can just plot those, and they're closer to the line in the middle of the relative humidity scale. And what this indicates to us is that a slope of 0, a line with a slope of 0, is not the best fit line. So then the question is, how do we find that best fit line? The best fit line is going to end up looking like this, but how do we parameterize this line so that it is the best fit line? So we can figure this out. We're trying to estimate an equation that will predict mass loss given some relative humidity. That relationship is determined by the y-intercept A and the slope value B. Well, the way that we estimate slope is by taking the sum of the x and y values and dividing by the sum of the x values squared. And so what we can do in this data set that we have, and I'll be posting the Excel file that has this all worked out, is x is the deviation of each x value from the mean of x. So this goes back to basically the sums of squares. We're going to calculate the deviations. When we calculate those deviations, they sum to 0. We could do the same thing with the deviations from the mean of y, and they sum to 0. But when we square the deviations from the average of relative humidity, these things actually add up to 8,301 rather than adding up to 0. So this is just the sums of the squared deviations of each of the relative humidities from the mean of relative humidity. X and y, as they're shown here, the little x and the little y, these are the deviations from the mean. When we multiply these together, what we get is these values here, and those all add up to negative 441.818. Recall that the slope value is the sum of the x times y values divided by the sum of the x squared values. And so it would be minus 441.818 divided by 8,301.389. And when we do that calculation, we arrive at a slope of 0.0532, and it's a negative slope. So we've calculated what the slope of the line is, but now we need to know where to anchor that line on the y-intercept. And so to do that, we just plug in the mean value of the weight loss, the mean value of y, the mean value of relative humidity, and the slope value that we just calculated. And what this basically tells us is what is the y-intercept in this case. So A is the y-intercept when you plug in the mean of y, the mean of x, and the slope value. And when you do this, you find that the y-intercept is 8.704. And you see from this line of best fit that I've calculated that the y-intercept is just shy of 9 up here, which would correspond to 8.704. And so it's not a terribly steep slope. A negative 0.05 slope is not terribly steep, but it seems as if this is probably a slope that is significantly different from 0. When we do this, we now can look at the residuals, the distance that each data point is away from the predicted best fit line, and we see that these residuals are much smaller than the residuals that we calculated with a slope of 0. And so a best fit line is the line that fits through the data in a way that it minimizes the sum of the squared residuals. So if you took each of these residuals, squared it, added that up, it would equal a sum of squared residual. And if we change the slope of this line a little bit, either making it a little bit steeper or a little bit shallower, we would find that the squared sum of the squares residual would go up. And so that's kind of the very definition of best fit line. So now we have to actually test whether or not this regression is significant. Is the slope of this line significantly different from 0? And that's what the other half of this spreadsheet is about. We can calculate the predicted values by basically plugging in the equation. If we have 0 relative humidity, what's the expected value of mass loss? And we do that by plugging 0 into the equation that we developed earlier that has a y-intercept of 8.704 and a slope of negative 0.053. Now we can look at how does that predicted value differ from the actual observed value. And so this is y minus y hat, and it's simply the difference between 8.704 and 8.98. Once again, these things are all positives and negatives, and if they are true residuals, they will sum to 0. And we can square those residuals, and when we square those residuals, this becomes 0.616, and that is the sums of squares residual. And so we're basically asking ourselves, what is the deviation of the observed value from the average value as this average value varies across x? One way of thinking about a regression line, let me go back. One way of thinking about this regression line is this is the regression line that represents the average weight loss as relative humidity changes. And so when we think about these predicted values are the running average of what you would expect weight loss to be as x changes. But that's what you would expect, but this is what you actually observe over here. So that deviation between what the mean is and what the actual data points are, that's essentially the numerator of variance once again. And so we're just defining a particular type of variance. In this case, the variance that we are defining is the residual sums of squares. But we also want to know how much of the variation in the data is being accounted for by the actual regression model. Well, to know what the regression model is accounting for, you basically look at what the predicted value is, because that's what the regression model is defining, minus what the average is without thinking about the regression model. So this would be y hat, which is the predicted value, minus y bar, which is the average value over here at 50.398. No, sorry, which is 6.022 rather. So 6.022 differs from 8.704 because there is actually a deviation from an expected line of 0 due to the regression model. So we can calculate those residuals. Like all residuals, those will sum to 0. When we square those residuals, they will sum to something other than 0, and that is the sum of squares regression. So we can take the sums of squares regression, we can take the sums of squares residual, and we can put that into an ANOVA table. The regression model has 1 degree of freedom because you're basically estimating 2 parameters, the slope and the y-intercept, and so you have 1 degree of freedom. You have 7 residual degrees of freedom because you had 9 total sample sizes, and your total degrees of freedom is 8. So then we have the sums of squares from the previous slide, 23.51. We have the sum of squares residual, 0.616. This is the mean squared. That is the F. That is a gargantuan F, which means that your p-value is 7.82 times 10 to the minus 7th. I calculated everything except the p-value by hand. You could go to a p-value calculator and get what the p-value is associated with this F statistic, or you could just calculate that in R. But the way that I did it was I just ran the statistical model in R. So I'll show you some R code here. Up here at the top, I've defined model 1 as a linear model defining how weight loss is affected by relative humidity, and the data frame that I'm using is the Beatles data frame. And when I type in summary model 1, it gives me a bunch of stuff that doesn't look anything like an ANOVA table. It basically reminds me what is the formula that you were using to calculate this. Then it gives me some descriptive statistics about the data set in terms of the residuals. But what you're really interested in is this section down here where it gives you the coefficients. So it gives you the intercept, which is 8.704, which is what we calculated a couple of slides ago. And it also gives you the slope value. How does relative humidity relate to weight loss? That's negative 0.053222. It gives you standard errors for these, and it also gives you the p-value for each of these. And once again, you can see that that's 7 times 10 to the negative 7th. But down here, you will also see that we have a thing called an R-squared value, which we're going to talk about in a few minutes. And we also have the F statistic, which is 267.2, which is what we calculated here. And we also have the degrees of freedom, which are 1 degree of freedom for the regression model, 7 degrees of freedom for residual, and then there is the p-value, 7.82 times 10 to the minus 7th. You can also run summary.AOV on model 1, and that will give you the ANOVA model the ANOVA table that we calculated by hand. All of these numbers correspond to all of the numbers that are in the ANOVA table that we calculated from the Excel spreadsheet. This tests the significance of the slope. See how this is relative humidity. That's the slope value. And so what it's basically telling you is that the slope attached to relative humidity is significantly different from a slope of 0. Now, when we look at the summary output from the entire regression, you see that there is this thing called R-square value. R-square is essentially, it's sometimes referred to as the coefficient of determination. The way I think of it is it basically tells you to what degree is variation in the y variable, in this case, and to what degree is variation in weight loss explained by variation in relative humidity. And so one of the ways of thinking about this is what percentage of variation in weight loss is explained by variation in relative humidity. This will go from 0, meaning that the x value, the variation in x doesn't explain anything in y, all the way up to a value of 1, which basically means that variation in the x variable explains all of the variation in the y variable. This has an R-square value of 0.9745, which basically means you're way closer to 1 than you are to 0. So here are some figures that I created a long time ago representing an R-square value of 1. In this case, every point is along the predicted line, which means that if you know what x is, you know what y is. Here is a line that once again has a y-intercept that is slightly smaller, slightly different from 0, but the R-square value is 0.9, and it's because knowing something about the variation in x tells you quite a lot about variation in y, but it's not telling you perfectly what y is going to be. As the spread of the data points gets further and further away from the line, as you get more variation around the line, you see that the R-square value goes down to 0.69 and down to 0.4375. So R-square value is a measure of variation around the best fit line. To what degree does changing x explain variation in y? This becomes important because sometimes you get regressions like this. This is from a paper that was published in Evolution back in the 1990s. This is relating the tail length of female birds to the tail length of male birds to see if those two characteristics are related in birds that pair with one another. Do long-tailed males tend to mate with long-tailed females? And what you can see when you look down in the figure caption is that you will see that the p-values for these regressions are quite high. And so I'm just going to blow up the caption for you because I want to pay attention to some things that are important. So it says here, tail length of female barn swallows in relation to the tail length of their mates. Absolute tail length. The regression equation is female tail length equals the y-intercept plus the slope value multiplied times male tail length. The F statistic for this is 33.05. The degrees of freedom are 1 degree of freedom for the regression model and 336 degrees of freedom for residual. The p-value is less than 0.0001, which would make you think that the regression is really, really significant. And it is in a statistical sense, but the r-square value is only 0.09, which basically means that variation in male tail length only accounts for about 9% of the variation in female tail length. So male tail length, even though it's significantly correlated with female tail length, male tail length is not terribly predictive of female tail length. And it would be nice if a significant regression was actually also very predictive. But it isn't, and what tells us that it's not very predictive is the low r-square value. You see for the other plot, the r-square value is even lower, it's 0.075. So the reason that this regression is significant is because this researcher has killed this regression with sample size, has a very, very high degree of freedom for residual, which reduces the residual sums of squares, which makes it really easy to see small deviations of a slope from 0. So look up here, the slope value is only 0.17. And so, why is my arrow not coming up? Stop it. Come on now, there we go. So here we see the slope value here is 0.17. The slope value here is also 0.17. Those are not very different from a slope of 0, but you have a lot of data that allow you to detect that that slope is different from 0, but the r-square value also tells you that there's a lot of variation around the line. You've basically reduced the influence of that variation around the line by having 336 breeding pairs of birds that you've looked at. So this is one situation where you really do have to pay attention to the summary statistics coming out of your analysis, because you don't want to make too much of a significant regression that is significant because you have a gigantic data set that doesn't really tell you much about how the y variable behaves relative to the x variable. And with that, that is the end of this screencast.